this reference detector as rectified by these, multiplied or rectified by these two chips. That V02 signal is then fed into the power generating circuit. This is a resonant, whatever you call that thing, it's a DC-DC converter. And you set the voltage that comes out of it, you set that by a resistor chain here. Normally, okay, you have this resistor in series with that to ground, and this is a feedback loop. And you by setting the output level, you can control the power into the cap here. That means power into the laser. Now, what we do, this is open loop, okay? We can adjust this pot here to change that ratio and therefore change the voltage at this point, meaning the power into the cap, meaning the power into the laser. Now, when you feedback control, you take the reference output, which is proportional to the laser power, and you clip this feedback loop. You just put the voltage right into this term. This reference term tells you you get a certain amount of output here for a certain amount of input. For 1.2 volts, you get something like 25 volts, whatever is the output here, and that's what you want on the laser power supply. If you don't have enough laser power, then, well, you do have enough laser power, because let me say it a little differently. The input of 1.2 volts here determines the voltage that comes out, and that always is correct to correct power to the laser, or to the cap that charges the laser, because it's a feedback loop. If you don't have enough laser power, you don't have enough voltage here, so it pumps more into it to get you to this level. I'm not explaining it too well, but one more time. You're breaking this resistor chain feedback loop, and you're putting in a direct voltage here of 1.2 volts, which incidentally, this is what this chain does. It wants to put 1.2 volts here. Now you're putting it from the outside into there, and that 1.2 volt at this point assures that there's enough power going to the laser. Okay, so now what we do is we clip.
Can you do it one more time, Alex? I'm sorry. You clip
this. You clip this resistance. See here, this. I bent this up a little bit. This resistor here, I clipped it already. I snipped it at this point here, right here. And now one leg is open, and I'll just unsolder that one. Okay. So now I take the white wire here. I'll go from the output of the sample and hold, which is the same point that goes to the reference signal V02. I go from that output to this point here, which is this particular point. And
which point is it?
This is the point here, right here. This here. Inject V02 to closed loop. Okay, you inject it at this point. So this white wire goes from, that's not shown, the output of the sample and hold, which is on a different board, goes to this point. Okay, so let me do this. Maybe we should put this thing on. Okay. Soldering a little bit, a little solder here.
You're right to the pin?
Yes, right to the pin. sure we don't show it out there. The next one, that's what we're playing this by ear, you know, but tomorrow I have a commitment to go somewhere. Okay, see this? I think we had one wire soldered to pin number 5 of the sample and hold, the LF398.
Yeah, if he calls in, I'll remind him.
The other is soldered to this resistor here. I'll tell you, identify it in a minute. It's the point that I showed on the drawing. Alright, it's fine. So, this should work now. So if you lay this back in. Alright, now it's the question of assembling the unit again per division. These are 1.2. It overshoots a little bit. If you look, you see actually it wiggles a little bit about. See that? The signal goes up, it wiggles a little around, and then it's steady. That wiggle is really, it needs a certain number of pulses to, there's a time constant in this thing, so it needs a couple of pulses to establish an equilibrium. It's not a continuous signal, so you have a whole lot of laser pulses individually, and you have a feedback loop that is strange, that instead of having a continuous feedback signal, you have a whole lot of pulses that integrate, but it's not really a full, not really DC, it's like a pulse kind of a thing, and you see the system wiggle needing, that means it needs a few of those laser shots to regulate. Anyway, that's what it is. I'm closing it up now. This is the standard procedure.
Where are you measuring from, Alex?
I measure V02. That is the reference signal that goes into the DC to DC converter on this H board, on the computer, on the pulsar board, the laser pulsar board. And this 1.2 volts here is really the V00, the reference voltage from the reference detector. That also goes into the computer. You normalize the returning laser signal with that. It's the outgoing laser power, but you keep it constant. Still, it goes into the computer because there's small little changes which you want to, normalize out. But the main point is that you are keeping the laser power constant, regardless of what the ambient temperature is, because laser output depends very much on ambient temperature. Laser threshold depends on ambient temperature. So you've got to change the power into the laser to get constant output power if the ambient temperature changes. That's what this does. So once again, you look at that V02, the reference voltage, which also is the control voltage for the feedback loop. It's not shown. Alright, this is this goes in front of here, and it has a mechanism whereby, I have to put it on right, but as you rotate it, it moves this in and out. Alright? It's just like a camera, exactly like a camera. Right? Now, I'm just showing you what's on here. You got, first of all, you got this needs, some more additional information. We have it on a modified drawing, but I'm just showing it here. There is a cold mirror here, a hot mirror here, sorry. And there's a cold mirror here. And the light comes in this way through the front lens. And it would be bent 90 degrees down here onto a pinhole. This is a pinhole. See it? Small pinhole. And then it is from this pinhole, it is, and I'm showing this over here from back drawing. See? There's a part in here. Just take this out.
404 and 440. 804 and 814. No, this is the time.
Oh, I see. These things. Why are you showing like that? Take it apart so you see it.
Gonna be in the film.
Yeah, and now this is going to be on film.
Okay. You have up on top here comes a beam folding mirror here. Okay. Light goes in here, gets directed. The reason for this is simply you didn't want to make this too long. If you had this in the back, the whole instrument would get too long. This beam folding optics is designed to make the instrument more compact. Right, so you have this mirror on top here, like that, which redirects the radiation 90 degrees. Then you have a pinhole in here, goes in here with a screw at this level.
Mike, look at this sheet.
Well, no. There we go. And then the next thing you have, and we have to refer to over here because we're showing this from the back, we have an item that looks like this, which is a lens. And I'll show you in a minute the optical layout, and you see better. You have a lens and a filter, and another lens. That this lens picks up the light that comes through the pinhole and makes it parallel. So it goes through a filter as a parallel beam. It's this lens which focuses it down to a detector. Let me just lay it out here on make a drawing. Are you familiar with optical schematics somewhat?
Yes.
All right. Okay, here's a lens. I'm just showing you optics. There's a lens. It's really actually a doublet. And it focuses light down. Now it would go to a point here, but with this mirror here, it focuses down to this pinhole here. Okay? And the light goes through the pinhole. And there's a lens here that picks it up, makes it parallel. It's called collimating. Collimating is making light parallel. There's a filter here. And then there's another lens which concentrates this light on the detector. Now, next thing you have is a laser that measures, that goes out and gets reflected from the target and measures the degree of blackness or whiteness of the target. If there's a lot of reflection, then it is white. And if it's white, it has a low emissivity. And if it's black, it has a high emissivity. And that is independent of whether it's red hot or not. So if you look at a piece of something in a furnace, it's red hot. But, so you don't know what its real color is, right? But this instrument doesn't care. It measures it anyway. All right, so now how do we do this? Well, we have, starting like backwards, because it's easy to draw. And let me draw it first, and then I explain. We have a laser beam like this here. It's a laser. It's a laser. It has a center, to input a power lead and a ground lead. The laser is on this ledge here. There's a little chip there, and that, in other words, if you're looking at this here. The magnifier. So, with the magnifier, you have to ground yourself to do this. We need you to ground. By the way, I did something that you should never do. Whenever I have a piece of optics or anything, I lay it on the table and have the other person pick it up. Never hand it in midair. You got it? I got it. Boom. There it is. You see that? Let me take a look at that too. We'll make sure that you can even see the wire here.
Out on that side.
Yeah. You have a little chip there and a wire to the top, and the beam comes out like this. So if you flip this like the other way, beam looks like this in one direction, and if you look at it like that, it looks like narrow in the other direction. So it's like an elongated beam. Now, this beam, as it goes out, is collimated again by a lens in here, by this lens. Okay, the lens is over here. This is shown in this picture over there. Laser beam, collimated, and here you see this lens makes the beam parallel. And there's a filter here. It's exactly the same filter as this. 904 nanometers. Just beyond the visible. And then after that comes a beam splitter that's not shown here. The beam splitter is in this picture is like this. That's the beam splitter here. I'm going through it a little fast, but you see you have this, and then you have a beam splitter that looks like that. Okay? Like this here. And what that does, it takes some of the laser radiation, a little bit of it, and reflects it, like 10% is reflected at the right angle. 90% goes through. But 10% is reflected and is detected here. This is a detector here that is a reference measurement. So you want to know how much laser power goes out, how much goes back, and the ratio is proportional to reflectivity. So now, this goes in like here. They both go into this thing. This one goes first. Okay. Such a way that it's coming out. Beam comes out this way. If you would shine light in here, it comes out there. Okay. And this thing comes in after that. Then you have two rings. One ring, another ring, and you have three screws. And the idea of this is to have the laser move around here so you can adjust the laser. Okay, by adjusting the laser sideways, back and forth, this way, and in and out, you can direct the laser beam. Okay, the laser beam, if you have a lens here, and you have a target here, or beam, a laser here, you move this over here, the beam moves over this way. You move it up, the beam moves down. So by moving it in this plane, you can align the laser beam. So there are two things to do. One is to get the position of this lens right. See, this has to be in the focal plane to make it a collimated beam. So we have a provision here. Oh, I didn't put it in right. I'm showing it this by itself. It has here a hole. You see a little dimple, called a dimple. And when it gets here, just give me a second and I'll put it in right. There it is. This really is easy once you've done it. See this here now? I can move this back and forth. So, here you go. See, move it back and forth. Like this. That allows me to focus, because if this lens is in the right position, and this thing is focused in such a way that it makes a focus spot at a distance. We look at that with the infrared camera. We focus the optics on this target over there, and then we adjust this thing back and forth until we have a sharp image. Okay, that means we have adjusted the focal distance properly, and then we adjust the laser in here to aim it exactly at the center. Now, I showed you how the basic functions here. There's one more thing, one little thing here. This is the mirror that bounces the laser out. See this here? The system goes like that. This goes in like this. Okay? Laser goes like that, and it bounces. Well, in this picture here, it's like sideways. It bounces the light out this way. And the real trick is that you see you have a stripe here. The laser beam is small. in this particular direction. The laser is aligned in such a way that the beam is sort of long, narrow in this direction and long in the other direction. So the beam only comes onto this area. It doesn't go onto here. And but the reflected beam goes through the outer areas. Okay. Now, there's a second mirror as you see here. What does that do? Well, that second mirror is called a cold mirror. This is a hot mirror. I know I'm rushing through this fast because this comes, over and over. But this here is the cold mirror, and this here is the hot mirror. Hot because it reflects infrared. Cold because it reflects visible light, which is the cold light. Okay. The reality is visible light comes from a hot source. Well, nomenclature is stupid, but in the movie business, you see, they have mirrors to bounce away the heat from the lamp. When you have a projector, you want the heat to stay away from the celluloid, because in the old days, it would burn, it was acetate. So it was very important. So they had a beam splitter, which was called a cold mirror, which would bounce the heat off to the side and let the visible light through, because that's what you need on your projector. This is where it all comes from. And they call it the cold mirror because the hot stuff was transmitted in this particular case, and the cold one was reflected. So, just like here, the visible light is reflected and the hot one is transmitted through. Never mind that visible light comes from a much hotter target than infrared, but that's another story. So you have a mirror here that bounces the visible light up. See, everything is on the same axis, so we still have the same direction of these things, right? So this one goes like that, and it goes onto a screen. We have a screen here that you have in your camera. You've been fooling with cameras ever? Maybe you did in your use. This is a screen, okay, which is where the camera forms an image, and you're looking at that image. And then we have image erecting optics, because if you have a lens, you look through, everything is upside down and right side to the left. So then comes a prism here, which looks like that, and the ocular, the eyepiece, for your eye. Here's your eye. Okay. So these light beams, they bounce around like this, whatever. They come out eventually here, right side up. This is what you're seeing is the entire system. This is it. Okay. This is the whole thing, and the purpose of it all here is to get three axes on top of each other. You have the infrared receiver axis, and you have the viewing axis. This is you're familiar with from here, because this is what you do here when you have an optical viewer. Same problem. But here, in addition, you have a third thing, which is the laser, the outgoing laser beam. All three have to be aligned on the same axis, and this is what this particular procedure that we're going through does. But before we can do all that, we have glued various things, all these lenses and so forth. They're not hanging in free air; they're in holders and so forth. So this is all done, and now comes there's still a couple of things to look at. This here, let me put my bigger cuts on. There's another little detail here, which it's very tight here. Okay. See, this is felt in there. Can you see that? You look at a certain angle here. See the felt? Because some laser already. This is 98% reflective, but there's still a little bit of light that sneaks through. And you don't want, see, if you had a smooth surface, it bounces back here, goes into the detector. And since you are so close to the detector, whereas the target may be 15 feet, 16, 18 feet away, and you lose quadratically. So you lose in two dimensions, this way and that way. So you have a much, much weaker signal, so you must suppress as much as possible any reflective signal. And this is the old radar problems, where you have a big, powerful radar generator right here, and the enemy is 100 miles away, and you got a weak signal, and you got to make sure that you don't swamp your detector. In radar, they use a time mechanism. They don't turn the detector on until the outgoing pulse is out for a while. You can't do that here. Okay, we do it all at the same time, so we got to be very careful about the, this is glued with the miracle glue and a special fixture. Got a fuse fixture here. This is the fixture that your friend made, where we put this thing in so that, you know, that it doesn't put it like this. Yeah, first we put it in like this. And this mirror isn't there, okay? This mirror isn't there. We do this first, and then now comes the trick. The whole thing is possible because the other mirror is smaller. So he's got to step in here, this step, and then we do this. We have to do some fine tuning on that. I think we have to order them a little narrower and make a little spacer here. So because I had to file this a little. Anyway, then this goes in here. You have to open this up a little bit. Goes in like that. Because this springs together. And when the machine that it comes together, so this has to be lined up properly with it's almost lined up, then two screws go in here. So what we should do next is to put these two screws in. Okay, I'll let you do that.